Hey guys, my name is Richard, and today we're going to be talking about de Moivre's theorem. And de Moivre's theorem is something you would typically encounter in a high school pre-calculus class, somewhere towards the middle of the year, after you've learned about some of the trig identities, the double angle formula, which we will be using today, and when we will be talking about complex numbers. So de Moivre's theorem essentially states this. You take the cosine of an angle theta, add that to I times the sine of theta. You take this whole quantity and you raise that to the nth power. And that is going to equal, I'm going to write it down here, I want to write it over there, not much space, but we want to equal cosine of n theta plus I sine n theta. At first glance, it seems really intuitive, right? You just take this n, you distribute it to both of these cosines and sines. But mathematically, why does it work? When I first saw this, it works out really nicely, but I was pretty puzzled as to why this whole thing worked. And to solve that, that's what we're going to be doing today. We're going to prove de Moivre's theorem, essentially. So to solve that first, I want to point out that this number in the parentheses, this expression in the parentheses, is essentially the polar form of a complex number. So normally, we see complex numbers as a plus bi. But all complex numbers that are expressed as a plus bi can also be expressed as the cosine of theta plus I times the sine of theta. Or more accurately, there's an r on the outside as well to account for all complex numbers. But when de Moivre saw this, I guess r, if you take the whole thing raised to the n, the r to the n is a no-brainer. The stuff here, that's the juicy part. That's the part that we're looking to find out. So no r. But this is called the polar form of a complex number. So we go from rectangular form to polar form. How do we do this? How can we say that all complex numbers can be expressed like that? Well, a plus bi can be expressed as x plus yi. X plus yi, well, we can graph x and y on the rectangular plane. So we're really using a triangle, we're using the trig definitions. This is theta, this is theta, this is x, this is y, and this is r. xy, point xy. So if we say, what is the cosine? What is the cosine of theta? That's just SOHCAHTOA adjacent over hypotenuse, x over r. We multiply both sides by r, and we get r cosine of theta equals x. This we can plug back in later. We can also do the same thing with y. Sine of theta, here, let me box this. Sine of theta equals y over r, equals y over r, equals opposite over hypotenuse. So r sine of theta equals y. So if we plug these back in to x plus yi, we're going to have r cosine of theta, that's x, plus r sine of theta times an I there. There's an I. If we factor out the r's, then what we're going to end up with is polar form. We're going to get r cosine of theta plus I sine of theta. So we've just proved that all complex numbers can be expressed as polar form. It's polar form. So now that we've done that, we know that we can use all complex numbers in de Moivre's theorem. Let's prove de Moivre's theorem. So de Moivre is saying that for all positive integer values of n, we're going to be able to use this formula. So if that is true, let's start with maybe the simplest case. The simplest case being n equals 1. So if n equals 1, I'm sorry for my multitasking here, but if n equals 1, what are we going to get? It's just cosine of theta plus I sine of theta. The 1 doesn't really matter. And in that case, it is cosine of theta plus I sine of theta does indeed equal cosine of 1 times theta plus I times the sine of 1 times theta. So, de Moivre's works if n equals 1. Can we do something similar if n equals 2? Well, let's see. So we take the cosine of theta plus I times the sine of theta. And when we square that and we FOIL it out, when we FOIL it, what we end up with is the cosine squared of theta, plus 2i cosine of theta sine of theta minus, because there's the I squared, that's a negative 1. You minus that and you get sine squared theta. This equals this. This may look pretty scary, but keep in mind, if we rearrange this, so if we move it so that it says cosine squared theta minus sine squared theta plus 2i cosine of theta sine of theta. So we're just rearranging the terms here. If we do that, then we can use the trigonometric double angle identities. Cosine squared theta minus sine squared theta, it's just equal to cosine of 2 theta. So cosine of 2 theta plus this whole thing. Now if we ignore the I for the time being, this whole thing is the sine double angle. So it's sine of 2 theta. So that's saying plus I times the sine of 2 theta. It works. If we look at it, this squared equals this. We've taken the 2 and distributed it almost to both terms. De Moivre's theorem now works for n equals 1 and n equals 2. So we could carry this on if n equals 3. We could just take what we got here, this result, multiply it by the cosine of theta plus I sine of theta. And indeed, that would give us the cosine of 3 theta plus I times the sine of 3 theta, if we did that. But how do we prove that it works for all values of n? We can use a method of proving called induction. And essentially what we're saying is, assume that for one given value of n, cosine of theta plus I sine of theta to the n power gives us this. And we've already shown that that works for some values of n. So assuming that this works, and we've proved that it does, we just try it for n plus 1. And if we can prove that it works for both n and n plus 1, then we've proved it for all cases. And so we've already done that. We could go through the algebraically rigorous method of doing that, and we would indeed get that the cosine of theta plus I times the sine of theta to the nth power does equal the cosine of theta, the cosine of n times theta, plus I times the sine of n theta. So we've proved De Moivre's theorem. We've used some examples, and we've proved several examples. N equals 1, n equals 2, and if you want to do it as an exercise, n equals 3 would also work. And then we took it more generally. We said if we set n equal to a certain value, and we assume that it does give us this, which we've proved work for some values, and then we take it to n plus 1, and it also works, then we're good. And that is essentially the method of proving De Moivre's theorem. So we've really got the formula down. We've proved it, we understand it. What examples, like what problems can we use De Moivre's theorem on? So what practical applications or what mathematical problems can we solve? And that is what I'm going to tackle with the next video. Thank you.